Now, what we ended on Tuesday, again, looking at the bubble point survey of a binary system, methanol, water, and acetone. What I'm going to do is, for those of you, again, we're starting from scratch here. I'm going to ask you now to create a new stream. Okay, so actually start with a brand new case file. Okay, we'll call this March 2nd. In fact, I'm going to do that now. I'm going to save this as March 2nd training. Studio Basics. March 2nd, MAR2. Good. Okay. And I'm going to have each one of you add a stream. Okay, and in that stream, I'd like you to add acetone. Okay, so just type in acetone. I'll show you what it looks like, the name. There it is. Okay. So again, we're going to duplicate part of what we did yesterday, but we're going to go a step further. So we have now water and acetone. The units you should have are going to be moles. But we're going to change those units in just a second. So the unit should be metric batch moles. And by the way, I'm just setting my stuff up to be back to what you guys have, okay? So what you see on my screen should be what you have on your screen. Stream amount is 55.5082, temperature 25, pressure 1 atmosphere, water 55 moles. Okay. Now, and of course you have acetone in that white cell there.
Hey Jay, one thing out of curiosity, not to interrupt your flow really quickly, why the water is always defaulting at 55.5082?
Yeah, the number 55, this number is 1 kilogram. So if I were to change this to mass, so you can see it immediately, if I were to change this by units from moles to mass, you'd see exactly 1 kilogram there. And there's a couple of reasons to explain that. One is, you know, in the past, when OLI was a water chemistry software, we always needed to have water in a stream. And so water was always present. Another reason is because OLI thinks in terms of molal units, moles, but molal units, moles per kilogram of water. So 1 kilogram of water, it seemed like an obvious choice to enter it. The good thing is you can always make it 0. The not so good thing is that the water is always present, but usually having water present in in a stream isn't necessarily a problem, having that molecule there. So, but that's kind of like the history of it.
Thank you.
Good. I'm going to change my units back now. I think someone else just joined. Hey, Faisal's here. Wonderful. Faisal, we're just getting started. And we're starting a new case file. Okay. So what I'd like you to do, in fact, I'm going to start from scratch again. So, so Faisal, you're with us, okay?
Yeah.
So make sure that you've got OLI Studio open, a new case file. I labeled mine. I saved my file as Studio Basics March 2nd, and now we're going to add a new stream, just like we've done before. Always start with a new stream. And again, we're going to add acetone. Again, you show formula view, so I'm just going to go back to formula so you can see it. And then once again, I'm going to change my units. But the way we're going to change our units is by clicking on the inflow units here where it says moles. And all we're going to change is this row right here, the inflows. We're going to make that mass fraction. Inflow, mass fraction, mass percent, and press OK. And then we're going to add a survey. We're going to change the calculation parameter right in the middle of the grid here from isothermal to bubble point. Okay, we did a bubble point calculation yesterday. And we're going to do a temperature bubble point. So we're going to adjust the temperature. The software has got, it shows a red button for calculate, because right now it looks like we want a survey by temperature, but we're also selecting temperature as a dependent variable. So one of these two things can't exist, but that's fine, because what we're going to do now is we're going to change the survey by from temperature to composition. And once again, we're going to adjust acetone. So we go into specs. That opens up the survey options window. We highlight the acetone. We go to our survey range. It's already set to start at 0% acetone, end at 100% by 10% intervals. We're going to change this to 5% intervals. That'll give us 20 steps. We're going to press OK. We're going to go press calculate. And we're doing exactly what we did Tuesday. We're going to look at the plot, and sure enough, there is again our bubble point plot. Okay, nice and simple. But why am I forcing you to do this again? Because I want to do two things here. I want to finish creating the phase diagram, and I want to show you the feature functions of copy paste. Okay. So did anybody not get this done yet? Because I realize sometimes I work a little bit too fast. I've been using this software for too many years. Does anybody not have this plot on their screen right now? Good. Mariana, I never asked you. I should have asked you from the start. Have you used this software before?
Yes, I have.
Oh, perfect. Okay.
I have no.
So there's no problem in creating a plot like this then? You're comfortable with this?
Yeah, I just did it with you. So
Okay.
Thank you.
You bet. Good. Okay. All right. Now, this is really kind of like why I wanted to do this with you. We created this survey here, right? We spent time creating the specifications. There's a feature function in the software where you can right mouse click on an object and paste it, copy and paste it. I want to take the survey, right mouse click on it, copy it, and then paste it back into the stream. Make a duplicate of it. Calling the first one the bubble point versus acetone. I'll call the second one the dew point versus acetone. And then I'm going to click on the second one, change it from bubble point to dew point.
Hey, Jay, could you repeat how you duplicated that, please, really quickly?
Mm-hmm. Yeah. So the way, and this is okay, let me go through it. So you click on the survey, right? So you're highlighting the survey, you right mouse click on it, and that shows this drop-down list here, right? And the third option is to copy it. So you select the copy, or you click on copy, right? It brings it into memory. Then you right mouse click at the stream. So now you're going to be on the stream, right mouse click there, and then you can paste. Did anybody have any problems with that? And then what I did after that, was just to rename everything. Good. Now, once you've got that done, press the calculate button. And then go to the plot again. Okay. And then there is your dew point curve. So generally, when we do this training, and I'm just going to do it myself, you don't have to do it with me here. I'm going to bring up an Excel spreadsheet. Takes a second to come up here. Here it is. Good. I'm going to take the bubble point data. I'm going to just click on the plot, right? I'm at the plot level. I press Control C. Control C brings the XY data into the clipboard. And I then do Control V, paste it in there. Okay. Do the same thing with the dew point data. I click on the dew point versus acetone, click on the plot. Just to make sure I'm active on the plot, I click in the white area, press Control C. go to my spreadsheet, press Control V. Actually, you know what? Why don't you guys do that yourselves? It's worth trying at least once to make sure you can get there. Okay. Because again, taking data out of the software can be quite useful. So go to the first one, bubble point versus acetone, click on the plot, press Control C, open up a spreadsheet or something else. Doesn't necessarily have to be a spreadsheet, and make sure you can paste the data in. And if you want, you can do the same for the next one. But the reason I want to do it is because I then want to show you the phase diagram. Right? Again, we don't model this thing directly inside of OLI because we don't have we don't bring the two curves together. But now you can see how you can create that diagram. So you got all liquid here, all vapor here, and then liquid vapor in between. Questions about that? Okay. So the teaching point on that was that one, you can create phase diagrams, binary systems, even ternary systems if you need to, with the software. And you can copy and paste calculation objects in order to duplicate them inside a given stream or even across streams. Okay. And then lastly, you can copy and paste your results, survey results from the plot itself into an editor of some kind. Okay. And one last thing I want to show you is that the copy and paste doesn't just exist within a stream. I'd like everyone to add a new stream. Okay, can't add it when I'm at the survey level, right? It's blank. So click back on the stream or at the top level stream there. Add another stream. Right mouse click copy again on your boiling point versus acetone. Copy it and then paste. So you can see once again that you can still copy and paste from not just within a stream, but across streams. But there's a trick in this case, or there's a catch though. Notice that the acetone is not built in there. Right? That's because the chemistry is not pasted over, only the specifications. So copy and paste at the calculation level brings in your calculation specifications. The chemistry is not assumed. Okay? So what that may mean is I may want to do this with ethanol. ETHANOL. Now I've got my composition survey already set up. I just need to select ethanol as my component, and I'm ready to do my survey. Actually, there's more to it than that, but let's just stop there because I don't want to go any further with this idea. So let me just delete that. Good. Any questions about that, about copying and pasting? Okay, we'll keep on going. Oh, by the way, Brett, I think which one of you guys are working with EAQ framework as your default? Brett, I think it's you, right? You're on 11.0, or was that you, Dino? On 11.0.
I'm on 11.5.
You are, okay, good. Dino, I think you're on 11.0, correct?
Yes, I am. Unfortunately, AJ.
It's okay. What I want you to do is click at the top level stream again, right? Since you're working in a new file now, correct?
Yes.
Top level stream, chemistry, model options, and change the thermodynamic framework to MSE. Okay. That way you don't have to worry about managing what framework you're using in your calculations.
Okay.
But what that means, though, is that if you redid the acetone, you have to make sure you're still in MSE. You're just going to have to do that one manually.
Okay.
Good. All right. Okay. So that example that I just showed is, again, a thermodynamic example where we're changing temperature, pressure, volume, or enthalpy, or essentially it's that type of chemistry. We're not changing composition. We're changing the thermodynamic state of the system. Okay. What we're going to do now, our thermodynamic properties. What we're going to do now, though, is change our thinking and start changing the chemistry. So what I want to do first is take the same general idea we had Tuesday, when we were essentially adjusting the stream with so much caustic in order to precipitate a solid. But we're really not going to do that per se. We're going to take the same idea of setting the pH of the system. So what we're going to do is we're going to look at, actually we're going to look at the speciation of carbon dioxide in water as a function of pH. So that's the case we're going to do. And the way we're going to do it is that we're going to, once again, add a new stream. And also, again, in order to see the action panel, right, you have to be at either at one of these two stream levels. If you're at the survey level or a single point calculation level, you don't see the objects in the action panel. So let's go ahead and add a stream. Right? We're going to rename this thing pH type pH survey. Okay. You're going to add carbon dioxide, CO2, to the grid. And you're just going to give it a small amount, 0.001 moles, right? 1 millimole of CO2. You're going to add a survey. And you're going to change the survey type from temperature to pH. Okay. A couple of things I want you to notice. By default, when you select survey by, the software changes the calculation type. First of all, the calculation parameter grid becomes essentially enlarged. Calculation type is now fixed at set pH. Again, it asks you to enter either a target pH here, or since you're doing a survey, it knows for you to add it over here. It then tells you essentially what acid and base you're going to be using in the survey. Since we're changing the composition, again, we have to define what material is going to be added. So by default, OLI uses hydrochloric acid and caustic as a strong acid and base. It can always be changed. Okay. What you're going to do next is you're going to click on specs. And what the specs does is it opens up, again, your survey options window where you can manually change the acid or base. Essentially, it's the same information that's here. And then next, the survey range. Again, this yellow cell here, right, it's yellow, the target pH, because we're going to be looking at multiple targets. Right now, it's going from 0 to 14 by 1 pH increments. And just to show you how you change that, I want you to go from 4 to 12 by 0.2 pH increments. Okay. So we're going to do 40 steps across 8 pH ranges. You're going to press OK, and then go calculate. Now, the purpose of this example is twofold. One, to, again, show you the chemistry of weak acids, so you get a general understanding of how things behave in water, okay, compared to strong acids. And secondly, we're going to start using the plot variables to learn how to find things in the plot variable list. Okay, calculation is done. Took 5 seconds on my computer. I'm going to go to the plot now. Actually, before we go to the plot, let me ask, did anybody have any problems getting to this point?
No.
Perfect. Okay. Remember, speak up because we have time to get things corrected. Okay. Good. Now let's go to the plot. In the plot, by default, again, if you look in the plot template manager, you can see there's a little option called default plot. The default plot for a pH survey is the amount of acid and base added to the stream. Okay? But generally, we don't care about that. Sometimes we do, but sometimes we don't. So what we're going to do is we're going to replace these variables with something we think we're interested in, and that's going to be the CO2 speciation. So you're going to click on variables. The first thing you're going to do is remove the variables in the y-axis. And there are a couple of ways of doing that. If you click on the header right here, it highlights everything. And at that point, you just use the double arrows to get rid of it. Alternatively, I could double click on each one individually or highlight it and then delete. Now what we're going to do is, now that everything's empty, we're going to the liquid 1 phase. Liquid 1 is the electrolyte phase. And you're going to put into the Y1 axis anything that has the inorganic carbon in its species. So that's going to be the dissolved CO2, carbonate anion, the bicarbonate anion, and then the sodium hydroxycarbonate ion. You can see it's going to be small, but we're going to add it anyway. So those are all the ways that carbon can exist as dissolved in water. Press OK, and there's your plot. Okay, it's a nice symmetric plot. And the cool thing about this, especially from a water chemistry standpoint, is that this is a typical plot of what we call a diprotic acid. That means CO2 can give up 2 hydrogen ions. The CO2 essentially, when it reacts with water, forms carbonic acid, H2CO3. From that point of view, H2CO3, you can see those 2 hydrogen ions, they are given up at different pHs. So here, for example, where we have essentially molecular CO2, that's the equivalent of having carbonic acid, free carbonic acid. Okay. By about 6.3 pH, the concentration of carbonic acid and bicarbonate ion are the same. Right? That point actually is important because that's what they call the pKa of the acid. That's like your acid dissociation constant. That's the number you'll see like reported in a table or in, let's say, in a report somewhere, or maybe in a textbook. Okay. Then above 6.3 pH, the bicarbonate is the dominant ion. So this is what we call the bicarbonate buffer. Okay. Actually, the buffer is right here, but I don't want to get too technical right now about it. And then at pH of 10.3 or thereabouts, you have bicarbonate and the carbonate again. Now here's the free carbonate ion, and you can see at about 10.3 pH, their concentrations are roughly the same, or the same. That's called the second dissociation constant at 10.3. So since carbonic acid has 2 acids to give up, you have a pKa1 acid dissociation constant, pKa2, and the pKa1 is at this pH, or the value of pKa1 is 6.3 or 10 to the minus 6.3. pKa2 is about 10 to the minus 10.3. But other than that, what you can see is the relative concentration of the different carbonate species as pH changes.
Question, AJ.
Yeah.
Okay, so if we go back to the select data to plot tab, and you went all the way down to change in the y-axis and add all the species that result from CO2 dissolved in water. Instead of doing all that, are you able to add CO2, go to inflows, drop down CO2 and add CO2 to that, and the software will automatically understand all the resultant species that result from CO2 dissolving in water? Is that, or subspecies that will result from that, or?
Right, it's like a category you're looking for. The short answer to that is no. We don't have groupings.
Okay.
That's a good idea, though. I never thought about that.
Yeah.
All CO2, all whatever else, borates, whatever it is.
Yeah.
I'm gonna just make a note about actually providing categories like that. Give me a second. I just want to write that down. Groupings of MAT codes for species.
Yeah.
The report.
And the reason being, AJ, is that to the layman, let's say somebody's using this, not a chemist, not a material scientist, not a surface scientist, whatever case might be, not an expert like you, trying to just understand the pH evolution when CO2 is dissolved in water or some aqueous solution. All they have to do is just basically go to inflows and click on CO2, as opposed now they need to have a foreknowledge of all the subspecies that result.
That's right. It's a little bit too
Yeah,
much
so
to ask. Yeah. Mhm.
yeah,
Yeah, I like that.
yeah, it just
Yeah, we can do that for sure. And there's no reason why not, because that's just grouping. We already have the data. So cool. All right. Let me stop here and ask any questions about this calculation or about doing, again, what we did was a pH calculation, a pH survey. I wanted to show you how to set that up. But at the same time, what I wanted to do is at least just give you a glimpse of the way that certain acids behave in water. And since the carbonate is the most important weak acid in all natural waters, that was the most obvious one to show. And one
May I
other
ask you
thing,
something?
yeah, please.
Is something related with the format of the legend. Could it be possible to see it as the name, not as a formula?
Oh, sure. So one of the things one of the things we have again is a names manager. If you click on this button up here, where you can see when you hover over it, the name it appears as names manager. You click on it. What that'll do is it'll open up a names manager window. And depending upon how you want to consume your information, you can set that to be display name or what we call OLI tag name or formula.
Perfect, thank you. I thought that was only for the definition, but
Yes,
we
for
also could do it here.
Yeah.
Thank you.
And since I'm here, I should also explain that there's something called a names dictionary, where if you don't, let's say, like the way OLI is reporting names, you can actually create your own name. So if I were to put like CO3 ion, take a little bit of getting used to. I want to call this AJ's fave, right? Apply. Now you can see AJ's fave shows here instead. So again, you can always create your own names for things if you desire that. All right, cool. Any questions then about this type of survey? Okay, so at this point, what we've done is a composition survey where we've forced the phase envelope to exist, either a bubble point or dew point. And then we've done a pH survey where we've fixed the temperature over a pH over a range and then adjusted the acid or base that was required to get there. What I want to do next is a different one. This one's actually quite practical. It's an evaporation survey. What we're going to do is we're going to create seawater and we're going to evaporate it. It's going to be like a kettle evaporation. But what that allows us to do is a couple of things. One, it allows us to it helps me introduce to you what we call the object library. It also helps me introduce potential calculation failures that you can get, and also how to manipulate, if needs be, your solids selection. So what I want you to do now is go back to the top level stream, not because we're going to do anything with it, but just that way you're kind of like back at square one, at base camp. And what you're going to do now is not necessarily add a stream here, but rather I want you to click on View, Toolbars, and then open up the object library. So View, Toolbars, Object Library. Okay, and what you're going to see on the right-hand side now is a new panel called Object Library. There is a set of standard objects that are part of the OLI installation, and then you may have what you call your own objects if you've created any. So we're going to stay with the standard objects, and one of those objects is going to be standard seawater. Actually, it's going to be called seawater molecular inflows. We have to use that one. Sorry about that. So I want you to find the one that says seawater molecular inflows. And I think I can double click on this, right? No, I can't. So I want you to double click on that. And what that'll do is that'll cause a new stream to appear in your navigator panel called seawater molecular inflows -1. And what you'll also notice is that you're going to have a whole bunch of compositions, inflows here. The units are going to be mgs per liter. You may want to change that just to simplify things. Okay, and you have 1 liter of it. And what we're going to do is we're going to evaporate this. We want to see to what level of evaporation we can get. So, but the way I want to do this though is I want to eliminate complications that can occur from this so that we can just focus on the actual mechanics of evaporating. What I mean by that is OLI evaporates things differently if the units are volume or mass. Right now the units are volume, and there's a pre-calculation that the OLI, the software requires that I don't want to explain right now. So what I'm going to do, ask you to do right now is click on, at the seawater level, just click on the units manager and change the units to metric batch. Let's just make it mass. Okay. And we'll do it again. I do want to eventually explain the units conversion, but right now I want to eliminate any additional explanations and just focus on the survey study. So when I change my units to metric, right, batch mass, what I see is that the stream amount is 1,022 grams, and that's not just 1,000, but it's 1,022. That's because that's the density of 1 liter of seawater. So 1 liter of seawater weighs 1,022 grams. That's how that number came about. And that 1 liter of seawater contains this many grams of each one of these inflows. Next, what you're going to do is you're going to add a calculation, a survey. And this time what we're going to do a survey by is not by temperature or pH. What we're going to do, what's called the vapor fraction survey. Okay, so change the survey by to vapor fraction. And then what we're going to ask the software to do is evaporate the system by raising the temperature, by adding heat to it, until we evaporate everything. So what that means is you're going to go to specs. In the survey range, essentially it says you're going to start at 0, which means nothing evaporates, to 100% where everything evaporates. And you're going to go by, let's say, 2% intervals. So you're actually going to have about 51 calculations, 50 steps. Can't remember if this takes a long time, but let's just try it out. So again, after you set the vapor fraction, you click on specs. You're going to use the default setting for 0 and end, starting and ending, but you're going to change the increment from 10 to 2. You're going to press OK there.
Should we keep the vapor fraction mole percent or mass percent?
Oh, it's going to, yeah.
Both.
I think it's defaulted to moles percent. That's going to be fine. And I'll have to explain why that is in just a second. Okay, there's actually a limitation there. But I want to bypass that just for now. Okay, so what does that mean? Well, again, vapor fraction shows up here in the grid. The vapor fraction, the amount that we're evaporating, again, shows up yellow because we're doing a survey. It's not a specific amount, right? We're actually at 51 different values for this. And then lastly, we're doing this as a function of temperature. Okay, and we're doing it at 1 atmosphere. Keep that in mind, especially for you engineers that work in this area with brines. You know that depending upon how you evaporate, you can evaporate at vacuum conditions in order to get the lower temperatures, and as a result, get different solids that form. Okay, so right now we're going to use the default settings of 1 atmosphere, and we're going to use the default of temperature, and we're going to press the calculate button. Now, as you might expect, when we look at the plot, since we're doing a vapor fraction study, you can expect the x-axis to be the vapor fraction and the y-axis to be temperature, because temperature is the dependent variable. So now once it starts, you can click on the plot and you'll see the plot starting to generate. Okay. What you're seeing here as the temperature increases, as you evaporate more, is what we know as the boiling point rise. As you evaporate more and more water from the system, the salt concentration increases. The net effect of that is to cause is what we know as the boiling point rise. Salty water evaporates boils at a higher temperature than pure water. What you're going to see interesting is when you get to higher concentrations, right now it's fairly linear, but when you get to higher concentrations, you're going to see this hockey stick effect. Okay, but eventually it reaches another plateau because you start reaching what they call solubility limits. Sodium chloride starts precipitating out, and you're essentially at constant composition. While this is cooking along, anybody have any questions on this?
Yeah, Jay, well, what will be interesting here after this hockey stick, as you put it, develops, to see how much concentration of salts and other species will be present in the vapor space, in the vapor phase.
In the vapor?
Yes.
Yeah, that's doable.
Or the residual, I should say, or
No, you can stay with that because there's boron, there's silica,
Yep.
there is CO2. All those things have a volatility.
Yep.
So we can certainly plot that. Yeah.
And then even we'll basically trace water vapor content on the vapor space as well. So we'll have some water droplets. So we're trying to understand how much water is in the vapor state that's present there. If possible with this, I'm not sure if that's something we can do or not.
It depends on how you look at it. Right now, we're creating a essentially the phase envelope. I'm sorry, we're creating the conditions where we have two phases, maybe multiple or more phases present, depending upon how many solids we got. And there's a way of taking that information. But before I answer that question, I want to do this first, and then we'll look at how you're asking about the vapor phase. Let's take a look at the vapor phase after this calculation's done, and I'll show you how you can pull that data out. I think that's what I want to say. Well, I didn't say it a good way. Okay. Now, first of all, you can see in my case, it got to 98%. Now it's trying to calculate the last fraction, and it's getting stuck. And so I'm expecting it to fail, and I want to show you that so you can see the red text here. So it's still trying to, what it's doing right now is that it's going through a series of solver routines, trying to figure out if it can come up to a global minimum for the state when everything is in the vapor phase. And it can't, because theoretically it's not practical. I've got sodium chloride that has to be salt, not a vapor. Okay, so my request to it to take everything in seawater and put it in the vapor phase simply couldn't be done. In fact, the only way, if you think about it, the only way that could exist is if we had a plasma, where we essentially heated this thing up to like 7,000 degrees Celsius. So the sodium and chloride actually were sodium chloride plasma ions. Okay, and that's not what we're doing here, right? So in this case, with the very last calculation failed. You can see what I was describing as that hockey stick. There's a plateau here where salt starts to precipitate, but then of course it goes up even higher because you end up with what they call a bittern brine, a magnesium sulfate brine. So that's that. Always keep in mind that the software will try and achieve a global minimum on every calculation, but sometimes it's possible that you give it a request that it just can't handle, simply because it's not practical. In this case, it's not thermodynamically feasible. Now, but from this, I do want to explain what you do with this information. I've got this evaporation here. I see the boiling point rise. That's good. What else can we pull from this? And this is where, again, I want to have you guys rely on the plot and learn how to use the plot feature functions in order to get information out of it. One thing I'm curious about, especially when you look at something like this, is what solids are forming. So I want you to click on the variables to open up the window, remove temperature, and expand the solid section. Okay. Right now you can see there's probably about a dozen solids that are forming. There's also something at the very top called the dominant solids. The dominant solids essentially are the 5 most important solids, or components in this category. So the 5 most important solids are showing, if I were to select dominant solids, then the plot would show me the 5 most important solids that are in the system. And importance means in terms of quantity. But just for now, I want you guys to do this instead. I want you to click on each one individually. I'm going to change the names in just a second. Okay. I guess there were 10 of them. So add all 10 to the Y1 axis and then press the OK. I'm going to change my names back to formula so it's easy to look at. Okay. And now what you can see is, yes, there are multiple solids that form. Salt is by far the most important, as it should be. It makes up essentially about 90% of the of seawater, okay, of the salts in seawater. Now, the other place I want to go with this is to show you how you manipulate the database to see what you want in a fairly efficient way. Because I've got the scale here of sodium chloride being so much greater than everything else, I'm essentially collapsing other important information on that y-axis. So I have a couple of options here. One of them could be to right mouse click on any of the values, or in this column here, you see where all the values are for the y-axis? Just right mouse click in that region. And then there's an option called logarithmic scale. So right mouse click on the y-axis where you see the numbers. Okay, it's got to be where the numbers are, otherwise you won't see the log scale option. And set that to log scale. Now this is one way of addressing the problem of having multiple of having essentially a large dynamic range of solids. In fact, if you look at it on the y-axis, I've got 1, 2, 3, 4, 5, 6, 7, 8 orders of magnitude a scale here. So that's way too much to show in a linear scale. Okay. So that shows up by just right mouse clicking on log scale. Now let's reverse that. So right mouse click on it again and now get rid of the log scale. So we're back to linear scale. The second option is to right mouse click on the sodium chloride, find any of the objects of the symbols for the sodium chloride and right mouse click on it. And then select switch to Y2. Let's take the one that is just higher than everything else and put that into the Y2 axis. But now sodium chloride is over here on this side. And now I can see on the Y1 axis, the left Y-axis, more information.
Hey, AJ?
Yeah.
With cases like this where you have different solid species that has precipitated, do we have an option of a pie chart or a bar chart? Because those are, I found them to be extremely helpful with solid species that precipitate.
Yeah, I hear you. And the short answer to that is no. The longer answer to that, is that we made a decision over the last decade about, what is in the best interest of our customers for us to focus on. Should we focus on, the thermodynamics, or should we focus on like graphics or other types of, functions? And we decided that there are already graphic companies around that do things much better than we'll ever be able to do it. So let's focus on what we can do well, and we'll rely on the customer, or we'll ask the customer to rely on those other software products to make like what you're talking about, those pie charts.
Okay.
By the way, I create a lot of ternary diagrams, and I do that using Origin Labs. They've got or surface plots. They've got a great, essentially, I like their graphics package for interpreting data, and that seems to be the best solution for the industry. Is that we'll spend our time, like right now, Xingjiang rather, is working on the solver routines to make sure everything converges properly. To me, we help the industry better by him working on that than him working on a graphics package. So I hope you accept that in terms of where we see our position in the market.
No, that sounds good. Plus, you mentioned earlier this is easily exportable to Excel, so that's as simple as that.
Yeah.
Okay.
All right, cool. Okay, now there's a third way. So I'm going to now I want you guys to go back around. Sodium chloride is in this case is the open box. So I'm going to put the sodium chloride back into the Y1 axis to get back to where I originally was, right? The problem. The third thing you can do is right mouse click on the symbol again and just remove it, right? Rather than having to go into variables, just remove that phase. Okay, so essentially what I just did there with the remove was to go into variables and remove it from the grid or from the list here. So again, even though we're not necessarily the experts in doing graphics, we're still trying to provide enough feature functions that make it possible to interpret, let's call it a first pass, or maybe even, a semi-thorough interpretation of the results, okay, using a two-dimensional plot. Good. Now, I do want to, Dino, I want to get to your question about looking at data. What I want to do first is to take it into two pieces. One, you were asking about the vapor phase. And I think this is a great opportunity to look at the power of MSE. If we've got 6 people in the room, how many of you know that silica evaporates? That you should get a vapor phase with silica, right? Think about sand, right? Would you consider there to be SiO2 in the vapor phase? Or boric acid, right? A white salt. What we're going to do is, and what we're going to do now is actually look to see, well, what evaporated? So I want you to click on variables. I want to remove everything from the Y1 axis. And again, the best way of doing that is to click on the header to highlight everything and then remove it. Use the double arrows to remove it. And then I want you to go to the vapor section. You see there's a vapor section here? And I want you to add everything that has a vapor component. About 15 things. As you might imagine, we're going to have to go to log scale again, but that's okay. So now we've added every vapor species to the plot. And you're going to press OK. Okay, as you might expect, first of all, let me stop. Did anybody have any problem changing this thing to a vapor plot? And am I going too fast? Am I explaining things clearly enough? Okay, now as you might expect, water is going to be the dominant vapor component, right? So right away, I told you to add everything simply because we weren't going to distinguish from one from another inside the variable list. We were going to decide that on the plot at the plot level. So I'm going to right mouse click on the water curve and delete it. We don't need to look at the water here. Okay. What you see next is carbon dioxide. Right? So as I evaporate the carbonate, CO2 evaporates. Right? So now I've got a high concentration of CO2 in the system. And at higher temperatures, I see a little bit of boric acid. Now, again, I could delete the CO2, or maybe the first thing I want to do is, like I did before, right mouse click on the y-axis and show everything in log scale. And so let's just do it that way for now. And we're not going to go any further than this, other than to say that it's actually plausible for materials that you think that have no business in the vapor phase to exist in the vapor phase. Okay, and that's simply because they will exert a vapor pressure. And again, whether it's low or high, it's still a vapor pressure, which means that it could potentially be a molecule in the vapor phase. And the software has to at least capture that. But just to show you, how low they are, here, for example, remember I said there's silica in the vapor phase, right? Here's my silica right here, SiO2, right? 10 to the minus 73 moles of silica here, or grams rather. That's kind of like, 1 atom per Earth kind of concentration. So you can see, yeah, okay, sure, there's a vapor pressure, but it's so low, does it really matter? And the short answer is no. And again, what you do is you just remove them. Right mouse click on the symbol and remove. Same with the silica hexafluoride, the hexamer, the hydrofluoric acid hexamer. You can see that 10 to the minus 65. Yeah, really? Get rid of it. I don't need to look at that. But the idea here is that when you don't know what you need to look at, throw everything in there and then use the plot to figure out what's important and what's not important. So here you can see I'm just removing stuff now that I know or is not going to be important in my interpretation because the concentrations are just too low.
Hey, AJ, I have a quick question. So when you say silica exists in a vapor phase and other species here, because it exerting a vapor pressure and it's very, very, very low, as you indicated. So that vapor phase is not superheated, obviously. So you'll have some water droplet, you'll have some other species that exist in a solid form by very, very minute. It doesn't mean the whole system has sublimed into a perfect or plasma, like you say, gaseous state. Is that what we're talking about here?
That's right. Yeah, we're just talking about a vapor at 120 degrees Celsius.
Okay.
And that's it. But I'm glad you brought that up because there's another program inside of OLI. It's called a high temperature program where we've looked at supercritical water to understand how much salt or how much silica evaporates or essentially vaporizes with the superheated steam.
Yep.
But that's separate from this software here.
Yep. My dear friend who's a welder engineer, he's interested in that for the flux when it goes into a very, 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 very high temperature.
Yeah.
So
it's interesting stuff because, again, we do a lot of work with oil production, and high pressure steam is important in that process when you create heavy oil. And in some cases, they're trying to see if they can use superheated steam, above 650 Fahrenheit, for example, in order to get better performance. But when they do that, they, sure enough, as you said, they carry along inorganic materials that aren't expected. And that can eventually cause problems downstream. It's corrosion problems downstream. So,
unfortunately.
Yeah, unfortunately, yeah. Okay. Any questions then about, let's say, this example? Now, I brought in a lot in this example. One, we showed you how to, again, use the object library. Right? I did ask you to change the units here from concentration to grams, and I'll address that in just a few minutes when we get back from break. We did a vapor fraction survey, which essentially is an evaporation of a stream by adding heat to the system. We use the default specifications for the maximum evaporation, which was 100%, and that caused the last calculation to fail, simply because we wanted to show you that in some cases, how you set up a case may not be thermodynamically feasible. And by me putting in 100% evaporation, that's simply not thermodynamically feasible. Okay, at least using this equation of state. Okay, and then lastly, we manipulated the plot feature functions, looked at different variables. Also, we showed you how to vary, let's say, the parameters or the characteristics in the plot, including things like log scale, removing variables, things like that. Okay. All right, any questions about that? Okay, good. So we're going to take a break right now. It's 5 after the hour. And again, part of this training, there are 3 pieces to the training. 1 is to get you comfortable with mechanics. 2, give you ways of interpreting or consuming the data. And 3, giving you at least a brief glimpse of what's going on from a thermodynamic standpoint. Like I was talking before about the weak acids, right? How CO2, how the properties of CO2 and the speciation of CO2. And like we just talked, as Dino and I were just describing, vapor pressures of materials and how they can exist in the vapor phase. So anyway, so that's the basis of what we try to do in Tricks of Trade, or in this training class, give you a little bit of everything. Anyway, let me stop there. Let's go ahead and take a break. Let's come back at about 13 minutes past the hour, and we're going to continue on. We'll probably do one more titration or one more survey, and then we're going to get to the water analysis. Okay, see you in about 7 or 8 minutes.